Hi, and welcome to 4.4 Who Let the Dogs Out? In this problem, we're going to be doing things with net force, acceleration, equilibrium, all good stuff. Let's get to it. It says, one day, Doug, Jimmy, and Charlie decided to get together at the park with their dogs, Porkchop, Goddard, and Snoopy, respectively. If you don't get these references, you need to watch some 90s cartoons, all this good stuff. Well, Snoopy's from way before then. Anyway, the dogs all fight over a 0.5 kilogram chew toy in an epic, ferocious battle. Porkchop pulls on the toy with a force of 3 newtons west. Goddard pulls with the toy with a force of 10 newtons north. And Snoopy pulls on the toy with a force of 7 newtons 30 degrees south of east. Of course, Snoopy has to be different. Come on, man, let's go. Weird angle here. 30 degrees south of east, what is that? It says draw a free body diagram of the toy. Only include the 3 dog forces. I put this in here because you don't have to include the weight of the chew toy. We're going to be doing that in later assignments. So no FG, no force due to gravity, just the forces of the dogs. So it says, what is the magnitude and direction of the net force acting on the toy? What is the magnitude and direction of the acceleration? And then Doc Brown comes along with Einstein. That's a Back to the Future reference. And Einstein pulls on the toy and makes it go into equilibrium. So let's just start by drawing a free body diagram. In physics, it always helps. You get this weird situation going. Always helps to start with a free body diagram. All right, so you want to draw your box first. So this is part 1, FBD. We're going to draw a box. And then just start drawing forces coming from the center of the box. Let's start with Porkchop. It's a force 3 newtons west. West is to the left. So we draw, this is FP for the force of Porkchop is 3 newtons. Goddard is pulling on the toy with 10 newtons north. So when you're drawing these vectors, if you have room on your paper, might as well try to draw them somewhat to scale. So this is the force of Goddard, 10 newtons to the north. So you can see this vector is bigger than this vector. Snoopy is pulling on the toy with a force of 7 newtons, 30 degrees south of east. So first you have to find where is east. East is going in this direction. We'll draw it out like this. And we want to go 30 degrees south of east, 30 degrees below the eastern direction. And if we had a protractor, it might look something like this. And again, you want to keep it somewhat to scale. It's somewhere in between here, maybe. And this is 30 degrees right here. This is the force of Snoopy. Fs is equal to 7 newtons at this weird angle. It's not quite only in the x direction, not quite only in the y direction. It's a combination of x and y. Interesting. All right, and that's all you have to do for part 1. That's it for part 1. So let's box this off here. Part 2 says, what is the net force acting on the toy? Remember, net force just means the sum of the forces. So we want to add these 3 vectors together, add these 3 forces together. But, you know, since they're in x direction and y direction and a combination of both, it's going to be a little trickier than just doing like 10 plus 3 plus 7. We want to try to make all the forces going in either the x direction or the y direction, because this force is going in the x, this is going in the y, this is going in a combination of the 2. So we have to break this up into x and y components. This is Fy. Really, we should call it not just Fy, this is Fsy. And this guy is the force of Snoopy in the x direction, Fsx. So how do we do this? Well, this is a right triangle. Just like all the other vectors we've done in class, this breaks down to just a right triangle. Snoopy's pulling in the x direction to the right with a certain amount, and in the y direction down with a certain amount. And hopefully you know what the next steps are going to be. So Fsx is adjacent to the 30-degree angle, And we also have the hypotenuse. So we have adjacent and hypotenuse. We better use the cosine function. So I'm going to do the shortcut method here. Just fsx is equal to fs cosine theta. Fsx is equal to, well, this is 7 newtons times the cosine of 30 degrees. So fsx is equal to a weird decimal, 6.06. So we'll round that to 6.1 newtons. So this is 6.1 newtons to the right. Now for FSY, the force of Snoopy in the y direction, it's going to be, we'll use the shortcut again, Fs sine theta. Again, because FSY is opposite the 30-degree angle, and we'll use the hypotenuse here. You know, at this point we could use Pythagorean theorem since we have the other leg too, but I like to use the information that they give us so we're not relying on with this rounded data, 6.1. We don't have to use that in our calculation. So this is just 7 times the sine of 30 degrees, and you get 3.5 newtons of force going in the southern direction, down, south, negative. Okay. All right. So we're not even done though. That's just the first part. Because for 2, it says, what is the net force? This is just setting us up. Now we have some forces in the x direction. So what color should I use? We want to find the sum of the force in the x direction. So we're only looking at the forces in the x direction. So Snoopy's force is going 6.1 newtons to the right, and Porkchop's force is going 3 newtons to the left. Both of these are acting on the x-axis, so we'll do 6.1 newtons plus negative 3 newtons. So the net force in the x direction is going to be 3.1. Okay, now in the y direction, we have Goddard pulling north, and part of Snoopy's force is pulling south. So let's sum the forces in the y direction. That's going to be 10 newtons in the positive direction plus negative 3.5 newtons in the negative direction. So the net force in the y direction is 6.5 newtons. If you add 10 plus negative 3.5, you get 6.5 newtons, right? So now we have a net force in the x direction and a net force in the y direction. Now we're ready to add these forces together. Let's draw them. So we're going to redraw. We could really redraw the box. We could make a new free body diagram. But now we're just going to include the x and the y forces, the net forces in the x and y direction. So this is 3.1 newtons. Fx, the net Fx is equal to 3.1 newtons. And the net force in the y direction is positive. The net force in the y direction is positive 6.5 newtons. So now we have 2 vectors acting concurrently, that means on the same point, and we want to add these 2 vectors together to get the total net force. So how do you add vectors? Head to tail. These are connected tail to tail, so we have to redraw one of the vectors. Doesn't matter which one, you could redraw both. And you want to draw in, here's the net force from start to finish. The bone is, or the chew toy is actually going in this direction. I don't know what happened there. Let's see. Alright, so this is the net force is equal to. Well, we're not really sure yet. Oh, I'm in my line function, that's why. Okay, we're not really sure yet. We got to do Pythagorean theorem. You could write it out, or you could just do, well, I'll write it out, fine. So a squared plus b squared is equal to c squared. 3.1 squared plus 6.5 squared is equal to c squared. We could have just started with this. C is equal to the square root of 3.1 squared plus 6.5 squared, and that is equal to 7.2 newtons. All right, so the net force is equal to 7.2 newtons. That's good. But it also asks for the magnitude, 7.2 newtons, on also the direction of the net force. So we have to determine, how do we want to name this direction? How do we want to describe this direction? So we could either find this angle here or this angle here. I prefer to find the angle with the horizontal. Doesn't really matter as long as you name it correctly. And we could do that right in this area. So that's the net force. Now we're looking for this angle, theta. Listen, you could do tangent, opposite over adjacent. You could do sine, opposite over hypotenuse. You could do cosine, adjacent over hypotenuse. We have all three legs of the triangle, so it's up to us with which trig function we want to use. I'm going to use the tangent is equal to the opposite over the adjacent. So the angle is equal to the inverse tangent of 6.5 over 3.1, and the angle is going to be 64.5 degrees. Now I would call that fx is in the eastern direction. This angle is going above the eastern direction, so I would say 64.5 degrees north of east. So here's the angle, and here is the net force. Very good, very good. All right, now this one is actually a little easier. Like, this was the toughest part, to be honest. You had to know how to, first you had to know to break Snoopy's force into x and y direction. Then you had to know, okay, now I have to do the net force in the x, the net force in the y. Then I combine the two using just head to tail. It's the same process that we've been doing. It's just a little bit more complicated because now you have this idea, okay, this is the net force in the y direction, and this is the net force in the x direction. Let me make my right triangle with those two legs. But then as soon as you knew how to redraw this, it's business as usual. You know how to find the magnitude and direction. And it's the same with number 3. It says, what is the magnitude and direction of the acceleration? So this is 3. 3 says, what is the acceleration? Well, they tell you the mass of the bone is 0.5 kilograms. See where I'm going with this? And the net force we just calculated is 7.2 newtons. So we don't actually have to do any of this crazy vector stuff because the net force acts in the same direction as the acceleration. We did the hard part already. Now it's just using Newton's second law. The acceleration is equal to the net force divided by the mass, which is equal to 7.2 newtons divided by 0.5 kilograms. So that's going to be equal to 14.4 meters per second squared in the same direction. So if we wanted to write it out, A is equal to 14.4 meters per second squared, same angle, 64.5 degrees north of east. And again, it's in the same direction as the net force. We already calculated the angle of the net force, so we don't have to do any more work with sine, cosine, tangent. We already did that. So basically, number 3 was impossible to do if you didn't know what number 2 was. Same with number 4. So number 4 says, Doc Brown comes along with his dog Einstein. Einstein sees his friends fighting over the toy and joins in. Einstein pulls on the toy with a force and brings the toy into equilibrium. What is the magnitude and the direction of the force that Einstein exerts on the toy? So for this one, you had to know what equilibrium is. Equilibrium is when the net force is equal to 0. So you could try to like look at this first diagram that we drew with all three forces acting on them and say to yourself, okay, can I visualize what force would need to be added to make this balanced? But I don't know why you would look at this diagram when you have this nice diagram we drew with the net force. All of these three forces basically boil down to this one force, 7.2 newtons, 64.5 degrees north of east. That's the net force. This is what you get when you add all three forces together. So for number 4, you want to think about the net force. The net force we already calculated is 7.2 newtons, 64.5 degrees north of east. If Einstein's going to come along and try to balance out these forces, and again, the net force is the combination of all three dogs. So all three dogs boil down to this 7.2 newtons. If Einstein's going to counteract all these dogs, he's got to exert a force in the exact opposite direction with the same exact magnitude. So the force of Einstein, or the equilibrium force, is going to be 7.2 newtons. And this would also be theta. I'm just going to write theta there. It's the same angle, 64.5 degrees. So the force of Einstein is equal to 7.2 newtons, 64.5 degrees. And then how do we name this one, right? So we were using north of east. But if we look at this angle over here, now it's going below west. It's going south of west. So 64.5 degrees south of west. All right, this video was a little bit longer than my previous ones, but as you can see, we packed a lot in there. This is a good question, and hopefully it makes sense to you now. Hopefully you tried it on your own first. Like I said before, this is really the tricky spot. I think finding, and this, okay, I have to find the net force in the X and the Y direction. All right, well, have a good day, and I'll see you tomorrow.